Number 6, we did number 6 pretty much in lecture, so you should see the notes in the lecture. This is conservation of mechanical energy, in which you have the initial energy, which is the potential energy, plus the kinetic energy. This is another way of writing down our equation 3 up there, which is equal to the final potential energy plus the final kinetic energy. And anywhere in here you can evaluate that. The work is the change in potential energy for a spring. So the work done by a spring is always that, the magnitude of the work, which if you have to calculate the work from here to a certain point here, well, is the area of this triangle, which is what is expressed in that expression. Now, if you have to calculate the work down in part B between a point here and a point there, which will be this area, well, that's the area of the larger triangle minus the smaller triangle, so it's still given by that expression. Then you have problem with a spring. In this problem, the potential energy plus the kinetic energy is always conserved because there is no friction. So at the beginning, it has mgh. When it comes in here and compresses the spring totally, it has 1.5 kx squared. In between, it has kinetic energy. But this is when it has a speed v here, horizontal is that. In between, it can have a different speed because it has a different height, which is what you can do for part A. This is what you do for part B. And of course, the energy is conserved. So you have to apply that concept there. The total work done here is the change in kinetic energy. Since you know the mass and the final speed, you know the change in kinetic energy, that's the total work. How much is done by gravity is mgh. And the difference between these two is the work done by air resistance. And the work done by air resistance, you have to be careful that it's negative. The magnitude of the average force is this work times the distance. This work is equal to the average force times the distance, so that's how you find it. And finally, number 10, you have another spring problem, which is this one. And first, you have the data in which the spring is hung vertically. And I did this today in lecture. So when you hang it vertically, then you have that the force of the spring balances the weight. So according to how much is stretched, remember this is the stretching by how much it stretches, not the length of the spring. So from here you get the constant K, and then once you get the constant K, you can apply it to here, to this problem, and the maximum speed, of course, is equal to the maximum compression. So that's all, and thank you very much.